Okay, we're doing Algebra 2, Lesson 35. And in this lesson, we're going to be talking about angles of a polygon. So we know right off the bat, if I have a triangle, angle A, B, C, the angles are going to equal to 180 degrees. So let's look at a quadrilateral. Quadrilateral from any two vertexes can be divided into what? Two triangles. They may not be equilateral or similar congruent triangles, but they're two triangles. And so this has to equal to 180. So this has to equal to 180. So the sum of a quadrilateral, angles of a quadrilateral, have to equal to 360 degrees. Now let's look at a fivagon or a pentagon, which is five-sided. So 1, 1, 2, 3, 4. So we can divide this into three triangles. So this sum is going to equal 180, 180, 180. So the sum of a pentagon, of their angles, of interior angles, is 3 times 180, or simply 540 degrees. So looking at this, we can say that to find the sum of interior angles of any polygon, we triangulate. Triangulate means to make it into triangles. The polygon from one vertex and multiply the number of triangles by 180. So we said for 3 sides you have 1 triangle to 180. For 4 sides we have 2 triangles and 360. For 5 sides we have 3 triangles times 180, which is 540. So each time we add a polygon side, we can draw another triangle. So a 6-sided polygon would have 4 triangles times 180, which would be 720. So we can use this little formula that says n minus 2 times 180 degrees. N being the number of sides. So if it's a 5-sided, we do 5 minus 2 is 3, and then multiply times 180, so their interior angles have to equal to that total, which is 540 degrees. Okay. Well, we can also find the sum of the measures of an exterior angle. If you look at your book, right above example on 35A, at the end of 35A, and it talks about the measures of the exterior angles of a polygon. And they're telling us they're 360 degrees. But they're going to prove it. They're going to show you a polygon, and I'm not going to draw the whole thing. Okay. So they've got the man walking. These are the angles. Okay, when the man walks all the way around, it's doing a full circle, so it's 360. Therefore, all the angles have to equal to 360. So if you look at example 35.1, it says find x and y. Well, they give us, you have to add all those angles. So you would do 65 plus 50 plus 40 plus 80 plus x plus 55 plus x all has to equal to, we said, 360 degrees. Well, then you combine these, so that's 180, 230, 285, and 2x plus, 290 equals 360. And then you just use algebra to solve for x. So x equals 35 degrees. Now I want you to find y, but if you notice this angle, you have x plus 55 degrees, and this is y degree. Well, this plus this, y plus x plus 55, has to equal 180 because they're supplemental angles. They make a straight line. We know what x is, so it's 35. We plug in 35 here, so it's 30, 80, 90. So y is 90 degrees. Okay, so we're going to move on now to inscribed quadrilaterals. So if quadrilateral, if a quadrilateral is inscribed in a circle, the sum of the measure of any pair of opposite angles is 180 degrees. So what do we mean? We say inscribed, so we have a circle. And if I have a quadrilateral, it doesn't have to be a square. This one turns out to be, but it doesn't necessarily have to be. We said the angles opposite, the sum of those two angles are going to equal to 180 degrees. Well, let's look at the example 35.b. They prove it. If you look at the first one, angle A is half, remember because it's an inscribed angle, so it's half of arc BCD. And if I look at angle C, it's half of arc BAC. And we said together they go all the way around, it's 360 degrees, but they're each half. So half of that, which is 180 degrees. So therefore this sum plus this sum has to equal to 180 degrees. So let's look at some examples. Example 35.2. It says find x, y, and z. Here's your circle, the quadrilateral, okay, and you've got 75, x, y, 80, this is 50, and this is z degrees. They want you to find x, y, and z. Well, what do we know? This is the letter z. This is 50. Well, this is 75. We know that from here to here is 150, right? So from here to here is 100 degrees, because 100 plus 50. All right? So we know that from on this, from here all the way to here is 160 degrees. So if this is 50, this is going to be 110. Z is 110. You see that? Then we got to find x. Well, what's the inscribed angle of x? It's from here, it's from all the way around to here. Now we know from here to here is 100. We don't know from here to here. But we know this is 110, 50, 100. So this plus this plus this plus this has to equal 360. So you have 210, 260. So this has to be 100 degrees. So we just need the arc from here to here, and we know it's 100 plus 100. So x is 200 degrees. Then we've got to find y. Well, we know the quadrilaterals. Well, we know the opposites have to equal 180. So we can find y. So it's 180 minus 75 is going to give us y, the y value. So y is equal to 105. There's all three angles. So I know it seems confusing, but you got to take what you know. They gave you 75. So what we did know, if we look at what they gave us, they gave us this is 75, which the inscribed angle is from here all the way to here is 150, because this is half of that. And they gave us from here to here is 50, so therefore this has to be 100 degrees. And then here they gave us 80, so from here all the way around is 160. We know this is 150, so therefore this has to be 110. So now we've got an angle from here to here, here to here, and here to here. We just need this last piece, and we know that it's a full circle, so that has to equal 360. So that's how we got this. Let's see, we got this to be 100 degrees. And x, the angle x, remember, it's from here to here. So it's going to be this arc all the way around. So it's 100 plus 100. So that makes this 200. And we can do one of two ways. We know that this plus this plus this plus this has to equal 360 because it's a quadrilateral four sides, polygon four sides, which is two triangles. Or we know that the sum of opposite quadrilaterals inscribed in a circle equal 180. So you could say 75 plus y equals 180. And that's how we got y is 105. Okay, so let's move on. Let's move on to the square root of 2, writing square roots. There's different ways of writing square roots. So if we want to write the square root of 2, we're used to this one. But we can also say 2 raised to the half power. That means the square root of 2. The same thing is just written and looks differently. If we say 2 to the 1/3, we're saying the cube root of 2. If we're saying 2 to the 1/4, we're saying the 4th root of 2. Okay, and the same exponent rules apply to the fractions as they do to regular exponents. So we have x to the 5/3 times x to the 8/3. What's our product rule for exponents? You have to have the same base, and you add the exponents. Okay, the only difference instead of whole numbers, you have fractions. You have to have a common denominator, which you do. You add the numerators, so it's just 13 x to the 13 over 3. What if I had x to the 5/3 raised to the 8/3? Well, how do we do this? When we have a power raised to the power, we simply multiply the powers. So you have x to the 5/3 times 8/3. Then you can't forget your rules for adding, subtracting fractions, and multiplying fractions. So this becomes x to the 40 over 9. Okay, how do we simplify? Again, you can't forget about your negatives. So you have 4 to the negative 1/2. Well, first thing, I want to get rid of this negative. So I'm going to change it to its reciprocal and say 4 to the 1/2, which is equal to 1 over the square root of 4, or 1 over 2, or 1/2 is my answer. So you just have to break it down in pieces. Let's look at negative 27 to the 1/3. Okay, well this negative is not protected by parentheses. To the 1/3 power. Sorry, I don't want. Okay, it's not parentheses, so it's negative 1 times 27 to the 1/3, and that's the same thing as saying negative 1 times the cube root of 27. Cube root of 27 is 3, so negative 1 times 3, or simply negative 3. Oh, I'm sorry, this was a negative 1/3. So the first thing. So we've got one more step. So what we're going to do here is we're going to change this to a positive exponent by doing 1 over 27 to the 1/3, which is negative 1 over the cube root of 27, which is negative 1/3. Didn't see that negative on the exponent. Now let's look at a little more complicated. Let's look at 16 to the 3/2. Okay? I can change this to say 16/3 times 1/2, right? Because a power raised to exponent is just multiply it, which 3 times 1/2 is 3/2. Or I could say 16, because of my commutative property of multiplication, it says it doesn't matter which way goes which. It still multiplies the same thing. Okay? So here, I could do the cube root of 16 first, which is 4,096 raised to the 1/2, which is the square root of 4,096, and use your calculator, you get 64. But can I take the square root of 16? Really easy. It's 4 and 4 to the 3rd power. Isn't that easier to do? You can use that to 64 without a calculator. So you can separate them and do which one is easier. It's easier to take the square root and then cube 4 than it is to multiply 16 3 times and trying to get the square root of that without a calculator. So, same thing, let's look at this problem. Negative 8 to the negative 2/3 power. Well, first of all, we have to remember that negative is not protected, so it doesn't go there. So you have 8 to the negative 2/3. So I want to take the reciprocal because I want to get rid of that negative exponent. So it becomes negative 1 over 8 to the 2/3. So now I'm going to break it up to 8 square raised to the 1/3 power, or I could make it 8 to the 1/3 square. Well, I know the cube root. That means the cube root of 8. So negative 1, the cube root of 8, and then square gives me negative 1 over 2 square, or simply negative 1 over 4. Negative 1/4 is your answer. So you simply just have to break it down. I could have done 8 square to the 1/3. 8 square is 64, and taken raise 64 to the 1/3, which is the cube root of 64, which will give me 4. I could have done that, but this was easier because I know the cube root. I like to work with smaller numbers, and I know 8 is a cube. All right, there is no code, and that is it for this lesson.